Cool. Well, thank you all for joining. As Alexis mentioned, my name is Denver Sorrell, and so I'll be talking to you today about managing serverless costs with Kubernetes. And so it should be an interesting talk today. We'll have some time at the end for questions, so feel free to drop those in the chat, and I'll address them at the end. So serverless is an extremely popular tool used to deploy and run workloads in the cloud. So what I hope to take away from the talk today is an overview of what happens when you run a workload on serverless, some of the limitations that can occur when running serverless and how they impact cost. And we'll walk through our journey of addressing some of these limitations and how we got more bang for our buck when running serverless. So now a quick plug for the company I'm at. I work at WP Engine. We provide our customers with a platform to build effortless digital experiences using WordPress. So whether you're building a landing page for your for a marketing campaign, or an e-commerce website for your clients, or your own personal travel blog, we allow you to just focus on your business, and we'll take care of speed, scalability, performance, and security. So now, what is serverless? So serverless is a pretty broad term. So just to clarify, what I'll be talking about today is specifically serverless compute, the most common of which is a function as a service. AWS Lambda was the first incarnation of serverless functions as we know it today. So I'll reference this from their website. As the name suggests, the idea behind serverless is that you don't need to provision any infrastructure. You just provide your code and what should trigger that code. And the serverless framework will take care of the rest. The biggest call out here is that you only pay for the amount of time that your code is actually running. The classic example of this is using an API gateway backed by a serverless function like AWS Lambda to implement a RESTful API that does CRUD operations on a database. So besides provisioning the actual database itself, using this pattern, you can implement a highly scalable RESTful API without deploying any web servers. Another great pattern is using a queue or a pub subtopic to trigger serverless functions. So while your applications are running, they can then publish events to this queue, like SQS, for example, or a pub subtopic like SNS, Kinesis, or Google PubSub. And then serverless functions can get triggered from those events. The cool thing about using this pattern is that you get a lot of great functionality right out of the box. You get auto-scaling, you get automatic retries for failed events, you get exponential backoff, meaning that you can wait longer before retrying failures on the same event. You can get deadlettering, which means giving up after max retries. All this great functionality is provided out of the box for you without writing any additional code. The cloud providers saw this pattern gaining popularity and added native integrations between serverless and other cloud services that they provide. So for example, S3 or GCS buckets can trigger serverless functions whenever a file is added, deleted, or modified in the storage bucket. DynamoDB, Firestore, and other NoSQL databases can also stream events that trigger serverless functions whenever data inside the database changes. So this led to serverless functions being widely used to deploy and run workloads. One thing to note is that because it's so easy to deploy and run, it can also be easy to run up a pretty big serverless bill. Running production scale workloads on serverless can at times come with some sticker shock. So let's look into what's needed to set up a serverless function. As we mentioned, you provide your code and a mechanism to trigger that code. But what's often left out is that you also need to provide the amount of resources you want to allocate to the function. So for serverless functions, this is generally the amount of memory you want to allocate to the function. Now let's assume we have a serverless function that gets triggered by an HTTP request. So now when that HTTP request triggers the function, The serverless provider will start up an instance to run the function on. Sometime after that, the code itself actually starts executing. Once that's done, assuming no other requests come in, the instance will die out. So now let's use this gray box to denote the time that the instance is running, and this green box for the actual invocation of the code. We're only billed for the actual invocation time. So now when a second event fires after the first invocation completes, the same instance will serve the second invocation. But what happens if a second event fires while the first invocation is still running? Serverless functions have a limit that an instance will only serve one invocation at a time. So the serverless framework sees this and starts up another instance to serve the second event. If we receive a third event after the first invocation completes, then we see that it can be served by the first instance itself, since it's now free. Now let's look at what happens inside the invocation itself. Let's assume that our code needs to make a call to an external API. And let's say that that API takes on average 500 milliseconds to respond. That's 500 milliseconds of execution time that you're being charged for, even though the function itself is doing nothing, it's just waiting. If the instance could serve another invocation, it actually has the resources to do so. But because of the one invocation per instance limit, it can't. Now let's assume that your function needs to read a file from a storage bucket, say, into memory. Let's assume that we allocate 128 megs to the function, and let's say that 99% of the time that file is small enough that 128 megs is more than enough to read the file into memory. But occasionally we get a big file, and when we read that big file into memory, we exceed the 128 megs that's allocated. The serverless framework will actually see this, and it'll kill your invocation. So because of this, we always have to over-allocate resources to be able to handle peak load, even though most of the time we actually want to use all those resources. So as we can see, these two factors combined can be the cause of higher than expected bills. We have to allocate more resources than we need to avoid the instance being killed. But we also have to pay for the invocation time while we're waiting on external dependencies. So these really boil down to the same root cause, which is the limitation of a single invocation per instance. The cloud providers have seen this, and they have an answer, which is to run containers instead of functions. AWS has a service called Fargate. Google Cloud has Cloud Run. Azure has container instances. These services allow you to get all the benefits that you get from serverless functions, but allow you to run multiple invocations in a single instance. What's even greater is that you only get billed for the time that you have at least one request running. So even in this example, these two requests overlap. You only get charged for a little bit more than you would for a single request. This allows you to make a lot more efficient use of the dollars that you're spending on serverless. Let's look back at our serverless setup. So what needs to change to be able to use serverless containers? The only thing that you need to do is package your code into a container image. This can be done using a CI/CD pipeline, and then you need to upload that image to the container registry, which your pipeline can do as well. Besides that, everything else remains the same. You still get all the benefits of serverless execution, auto-scaling, automatic retries, deadlettering. All those benefits you got before still apply to serverless containers. So now let's compare these two from a cost perspective. Let's assume that I allocate 128 megs to the function, and it runs for 1 second. And let's assume that 128 megs for 1 second costs $1. Now the real cost is obviously much, much lower, but this is just for illustrative purposes. So with that, the cost for serving these 3 events comes up to $3. With serverless containers, the same instance is able to serve all 3 events concurrently. Assuming the same cost structure, we only get billed a little bit more than $2 to be able to serve these same 3 events. Let's take this a step further. Looking at this workload, we get a cluster of 5 events at the beginning, and then another 5 events a little bit later. With the same assumptions as before, it costs us $10 to serve these events with the same dollar invocation per cost. But let's look at the serverless container option. We can serve all 10 events now with a single instance. But let's assume that we need more resources to be able to serve them all concurrently. Let's assume now that we need 256 megs to be able to serve these concurrently. So then my instance cost doubles. But my billable time has gone down from 10 seconds to 4 in this scenario. So my cost per invocation has gone down to 80 cents. So this shows how we can get a lot more efficient use of our serverless resources that we're paying for. So now while this is all good theory, let's move on to a practical example. So let me set up the problem here. At WP Engine, we host our customers' websites on servers in the cloud. And we partner with a company called Cloudflare to provide an additional layer of security to our customers' sites, which blocks malware, DDoS attacks, and other bad actors at the edge. Now, we'd like to be able to show our customers how many attacks were blocked for them. To do that, we used to have a Kubernetes service that would pull these events from Cloudflare. We would then augment the data in these events with data from our internal APIs, and then write that augmented data over to BigQuery, which is a data warehouse service that we use. It's provided by Google Cloud. In order to transition to a more event-based architecture, this changed to a structure where Cloudflare would push events to us as files on a storage bucket, and then that would trigger serverless functions to do what our Kubernetes service used to do. To give you an idea of the scale of the problem, every 5 minutes or so, we would get 1 or more files dropped into the bucket, depending on how much traffic was being served. And these files range from 300 megs to up to 4.5 gigs. The files themselves contain data about each request. They're blocked at the firewall, which firewall rule that can be blocked, and so on. And here are some numbers to show you the amount of traffic and amount of workload that we would get on a weekly and daily basis. Because the files themselves were so big, we couldn't just handle them in one go. So we split this up into 2 serverless functions. One function, which we call the splitter, that would break up the file into chunks and write it to a temporary bucket. Those chunks getting created in the bucket would trigger a second serverless function, which we call the BigQuery writer, that augmented the data in the chunk with data from our internal APIs, and then wrote the augmented data over to BigQuery. Here you can see the number of invocations per second for each of these serverless functions. The splitter would not get too many. It was essentially 1 request per file. However, as the splitter broke up the file into several chunks, these chunks generated a lot of load for the BigQuery writer. And as you can see in this example, we were consistently getting 4 to 6 invocations per second. And here you can see the number of active instances that stood up to serve that load. As you can see, the BigQuery writer instances would spike up to 80, and in some cases, several hundred instances to serve the workload. Furthermore, we could see that the number of instances would rarely go down all the way to 0, because it would keep getting more load added to it on that 5-minute cadence. And now let's look at the memory used by the functions. As you can see, the memory usage would also vary a lot. The BigQuery writer was relatively stable, but the splitter, on the other hand, would vary a lot depending on the size of the files coming in. And so we would have to over-allocate resources to avoid the function being killed. So we then started to use Cloud Run, which is Google Cloud's serverless container framework to run this workload. The top row shows the active instances for the serverless function compared to the serverless containers on the bottom row. The splitter didn't show much difference, but if you look at the BigQuery writer, you can see that we are able to handle events concurrently and serve the workload with way fewer instances. The number of concurrent requests an instance can serve is a knob that you can tweak. And the more concurrent requests we allowed, the more efficient we got from a cost perspective. So when we increase this up all the way, we were achieving savings of 6 to 10% on a day-to-day basis. If you could allow even more concurrent requests, we could probably achieve even more savings, because looking at the resource usage here, we would rarely go up to more than 70% utilization. Another thing we noticed was that the active instances would now often scale down to 0, meaning it would complete the backlog of work before the next batch of work would come in on that 5-minute cadence. So this led us to investigate what would happen if we limited the maximum number of instances that the container could scale up to. On the right, you can see the number of active instances when we throttle the Cloud Run to not be able to scale up to more than 5 instances. And as you can see, we were able to keep up the amount of work coming in. Furthermore, if you look at the resource utilization, that line is now a lot more smooth than it was before. So we are a lot more tuned to the workload than we were before. So now let's look at the savings. When we went from serverless functions to serverless containers, we achieved savings of 6 to 10% on a day-to-day basis. And then when we added throttling, this increased our savings up to 20%. So this demonstrates that using serverless containers is a great way to get a lot more efficient use of the resources that you're allocating to serverless workloads. But wait, there's more. With serverless containers, we're effectively running containers on cloud-managed infrastructure. But what about Kubernetes? Kubernetes is the de facto container orchestration platform in the market. And if you're using a managed Kubernetes offering, then the savings from serverless containers can be even higher. AWS allows you to run Fargate on EKS, which is AWS's managed Kubernetes service. The same for Cloud Run from Google, which allows you to run Google Cloud Run on GKE. Azure allows you to run Azure Container Instances on EKS. These are all relatively new offerings, some of which are still in beta, but they offer an exciting value prop in terms of cost. So what's the difference? The main difference is that the final billable amount that you get charged for serverless containers depends on 2 factors. The billable instance time, which is the green box that we've been seeing in previous diagrams, and this is the major component of the cost. A smaller component of the cost is the number of invocations. When you run serverless containers on a cloud provider's managed Kubernetes service, that first component essentially goes away. It's effectively covered by the amount that you pay for running your Kubernetes nodes in your cluster. So then you're just left with the number of invocations, which is a really small part. Just for context, if you're running Google Cloud Run, the cost per number of invocations is 40 cents per million. So it's really a small amount. So using a combination of serverless containers and managed Kubernetes allows you to achieve even more savings. And that's something we're actively investigating at this moment. So that covers what I wanted to talk about today. In summary, I hope you leave with a better understanding of the inner workings of serverless executions and the limitations that may be costing you money, namely the 1 invocation per function instance when using serverless functions. And we demonstrated how using serverless containers avoids that limitation, thereby helping you to get the most efficient use of your serverless dollars. So with that, I thank you all for your time, and I'll open it up to questions.
Hey, Denver. Everyone, thanks so much for joining, Denver. That was really fascinating. I definitely learned a lot. If anybody has any questions, put them in the chat box over on the side, and I'll be sending them over to Denver and asking them live. Got some coming in. Denver, is there a performance difference for invoking the Docker versus serverless function?
So what we've seen in our experiments is that it's almost the same. And really what you're looking at is the amount of time per invocation, and that's essentially the same. In fact, there's a slight benefit. If you're familiar with the serverless functions, you're familiar with cold starts, that's the amount of time that it takes to start up the instance. With serverless containers, because you're running many invocations on a single instance, you only get one cold start per instance. So it actually can help you from a performance perspective from cold starts.
Awesome. Does Azure's app service count as serverless?
That's a good question, Richard. I'm actually not familiar on Azure App Services. Specifically, what this one counts, I know that I think it's Azure Container Instances, which are serverless containers. And I forget the terminology for Azure's Lambda equivalent, but I can look that up and see.
Awesome. Oh, you already answered questions about cold start, so we're already there.
Cool.
Let's see, give everybody a few more minutes to see if there's any other questions that come in. How long of a process has this been to implement? This is just something that I'm wondering, like how long have you guys been working on this at WP Engine?
Essentially we already had this workload running as a cloud function, which is the serverless function equivalent. So, it was pretty simple. We just took that function, had a CI/CD pipeline that packaged it into a container and then ran it. And that was all it took to actually, change to this serverless container framework. A lot of time was just taken in terms of like experimentation to get, comparisons of CloudFunction versus Cloud Run. But actually converting it to a serverless container framework was pretty easy.
That's awesome. That something that can make such an impact is a relatively low level of effort.
Yeah.
And less.
Cool. If you don't have questions, Christian, I think I have a slide here around cold starts. I actually cut it for time.
Perfect. Yeah, let's jump into that because I know there's two other people who said you started to answer it. So
cool. So this is what cold starts look like for serverless functions. So you can see in that same, 5 events at the beginning, we have 5 cold starts, and then the rest are warm starts. And here's just some numbers. But if you look at serverless containers, you can run that all with a single instance. So then only your first invocation is actually a cold start. Everything else is warm starts. And because you're all running that in a single instance, that would be, performance benefits from a cold start perspective.
Yeah, perfect. Very cool. Two other questions have come in, and we have 2 minutes left, so we'll answer these 2, and then we'll have to wrap it up. But what do you think would be the point where you would want to make the conversion, or are you thinking it would be across the board?
So it really depends on the amount of benefits that you get and the amount of money that you're spending on your serverless function workload. If you're spending, on the order of like tens or maybe even hundreds of dollars, it may not be worth the engineering effort to make that conversion. But if you're running a production scale workload, that can definitely be, several thousand per month, for example, and then the savings would be beneficial.
Yeah, so it's just doing that analysis of the cost. Okay, awesome about, we don't jump too far down. What's the consideration on killing the container versus keeping it alive? Or do you always kill?
So it's actually the serverless framework that controls killing the container or keeping it alive. Whether that be Lambda or CloudFunctions, that's what controls it. And they sort of like keep an eye on, we were normally getting 10 requests a second. So now we're only getting 1 request a second, so I will kill it very quickly. Versus 10 requests a second, and now I've got 5 requests a second. Maybe I'm going to get some more in a little bit, so I won't kill it quickly. That's entirely managed by the serverless framework, which is actually a great thing for us because then we don't need to manage it.
Yeah, awesome. Let's see. Christian is saying, awesome about cold starts. We tend to get spikes of traffic that get killed on Lambda cold start times. Having some pseudo reserved instances like this would help a lot. So
yeah, Lambda actually recently announced this reserved instances, so then that you can like keep a certain amount running. And even with serverless containers, you can do the same. You can keep like say at least 2 instances running, so you're always being able to serve some, and then you only have cold starts when you need to scale up.
Nice, wonderful. Well, I think that's all the time that we have for questions. Thank you, Denver, so much for presenting and doing all of this and for including me to help answer some of these questions for everyone.
Cool. Thank you all for your time.